Welcome to this deep dive into Linux capabilities. Traditionally, Linux permissions were binary. You were either a normal user or the all-powerful root. Capabilities change this by splitting root privileges into smaller, named permissions. In this lesson, we will examine how these granular rights provide a more secure alternative to SUID, while also creating new, often overlooked surfaces for privilege escalation. We'll cover everything from kernel-level sets to specific exploitation patterns for over 30 different capabilities. The core idea of capabilities is the principle of least privilege. Instead of giving a binary like ping, full root access just to open a raw socket, we grant it only capnet raw. While this reduces the overall risk if a binary is compromised, it does not make the binary inherently safe. As pentesters, we must audit these capabilities, especially capsysadmin or capsetuid, as they often provide a direct path back to full root authority. The kernel manages capabilities through 5 distinct sets. The permitted set defines the maximum rights a process can use. The effective set contains the capabilities currently active for kernel checks. Inheritable capabilities can pass to child processes, while the bounding set acts as a hard ceiling that a process can never exceed. Finally, ambient capabilities are unique because they can survive an execv call for non-SUID binaries. Understanding these boundaries is critical when analyzing process behavior. Capabilities live in 2 places. For running processes, they are stored per thread in the kernel and visible via the /proc file system. For binaries on disk, they are stored as extended attributes. When you inspect a process status file, you'll see hexadecimal masks. These are not human-friendly, so we use the capsh tool to decode them into readable names. This allows you to verify exactly what privileges the kernel is enforcing versus what the program claims to have. Enumeration is straightforward. To find every capability-enabled binary on the system, use getCap recursively from the root. Focus on unusual paths and interpreters. To inspect a running process, use getCaps with the PID. This tool queries the kernel directly via the capget system call. Finally, capsh print is your go-to for checking your current shell's capabilities. Always look for high-risk flags like capdac override or capsysadmin. Exploitation varies by capability. capsetuid is the cleanest path. It allows a binary to impersonate root even if it isn't SUID. If an interpreter like Python has this set, you can spawn a root shell with a single line of code. Capdac read search allows you to read any file, including /etc/shadow, while capdac override lets you bypass write checks. This is devastating, as you can append yourself to the pseudoers file or overwrite sensitive configurations to gain persistence. The most powerful capability is capsysadmin. It is effectively near root, allowing you to mount devices or manipulate kernel features. In Docker environments, this is a primary breakout vector, as you can mount the host disk and croot into it. Capsystrace is equally dangerous. It allows you to attach to and trace other processes. By injecting shellcode into a running root service, you can obtain a shell without ever touching the disk. Always assume capsys module leads to full host compromise, as it allows loading malicious kernel modules. A common and confusing misconfiguration is the =EP syntax. In the libcap library, the equals sign sets the list to all. Therefore, =EP grants a binary every single kernel privilege. While the UID remains unchanged, the process has full power. Another risk involves ambient capabilities. Capability-dumb binaries don't drop unexpected privileges, so they will happily run with any ambient capabilities provided by the environment, inheriting power they were never designed to handle safely.
So let's start preparing the working directory. So we are going to create a directory right here, user local cap demo, and this is where we are going to work. So now we need to create the demo source file, the C program that we are going to use. It's a very simple program. It's this program right here. So what this program does, it mainly does two things. First, it prints the real UID and the effective UID, the same way we did at the previous demo. So we can confirm whether the program becomes root or stays as a normal user. And second, it tries right here to create an ECMP raw socket. That action is normally restricted, which makes it a really good text to check the capability cap_net_raw. So we save the program and we now compile it. So now that we have compiled the program, we exit and we execute it with the normal user. So we execute it, and here we can see that the program has been executed as the normal user and the action has not been permitted. So this is the expected failure, and this is the most important comparison of the whole demo. Now we go back to the privilege cell and let's change the capabilities of that file. So now we are root again, and we are going to make use of the set cap command, where here we specify the binary we want to change and the capability we want to add. So we are going to add the cap_net raw capability. Let's check that the capability has been set correctly. And here it is. We can see the capability we just added. So the P here means that it's permitted and the E means that it's effective. So in practical terms, it means that the kernel is allowed to grant this binary the ability to perform raw network operations when it runs. The important point here is what we did not do. We did not change the owner to root in order to use the SUID, and we did not make the process fully root. So we only granted one specific privilege action to this file. So now we do exactly the same as we did before. We exit and we run this program again with a normal user. And here we can see that the real user and the effective user still is the normal user, is not root, but the raw socket now works. We can see here that it was created successfully. This is because the kernel sees the cap_net raw capability on the file and allows that privilege action. So capabilities are much more precise than just the SUID. So instead of giving a program full root context, Linux grants just one narrow permission. And finally, let's run LinPEAS. So we execute LinPEAS and let's wait for the information to show up. Okay, we can see the SUID information, the SJID. Let's see here we have the capabilities. Okay, so let's go to the beginning of this section. Okay, so here we have these two first subsets of information, the current cell capabilities and the parent process capabilities. These are showing the capability state of our current cell and of the process that launched it. So here the fields that matter are these ones. So we can see the cap in, which is the inherited set. So it tells us what could be inherited across exec in the right conditions. Here contains the cap wake alarm, which is unusual, but it's not very interesting. So we can see also the cap PRM and the cap F. The PRM one means the permitted set and the F means the effective set. These two means that the capabilities that the current process can actually use right now. In this output, both are 0, so it's not very interesting. After that, we can see the cap BND. This is the bounding set, which is the upper limit of what this process tree is still allowed to gain later. So here is very broad. As we can see, there are lots of capabilities. So it is not heavily restricting future capability. And we can see the cap AMB, which is the ambient set. And here is 0, but so there is no extra capability being carried into child processes. After that, we can see that LinPEAS starts listing a lot of capability sets. This output can be really long, as we can see here. Because many root-owned systems processes naturally run with broad capability sets. So this part is useful as a background, but for a first pass, it's usually not the most actionable part of the output. But in the end, we should see something really interesting, which is this part right here, which is the files with capabilities. So here LinPEAS gives us the list of actual binaries on disk that have file capabilities assigned to them. In this output, for example, we can see the fping capability that has the capnet row, along with, we can see also the dump camp that have many other capabilities. We can see the example we used for this demo. So this is the part you can actually act immediately, because it tells you which executable has the capability and exactly which capability it has.